Right. Started right up. There we go. We'll start it there. And I'm gonna go ahead and share the screen, and we'll find out if anybody has any homework questions. We'll deal with that first. Okay. And by the way, it's Friday, which is a good thing. Oh, what happened?
It should be a good thing.
Can y'all see me?
Yeah.
Yes.
I can't see me. That usually bothers me, but I can't see me. Oh, well, whatever. This will come up in a second, I hope. Sharing is paused. You shared window to the front. Okay, come on, give me back. Give it back. Give it back. Okay. What's going on?
It says you have started screen sharing, but it's just blank.
Did well. It says it's It says it's paused, but I don't know why it's paused. Oh, resume share. Let's do that. Resume share. Tell me if you see it, because I'm not seeing things for some reason.
I just see Deborah.
Okay. I just see Tiara. I'm not even seeing Deborah anymore.
Yeah, no.
Now I'm seeing Alexis or somebody. That looks like Alexis.
423.
Somebody. I don't know who that is.
The 4 digits.
Okay, there you are.
Dion told me to tell you that
Yeah.
the Wi-Fi at her house is not
Wait,
working.
Alexis is trying to talk, guys. What? Say it again, Alexis.
That Dion told me to tell you that the Wi-Fi at her house is not working.
Okay. Oh
And
boy.
that like Zoom is not letting her log in on her phone.
Okay, that's kind of, yeah, I'm having a little bit of problems with Zoom right now too. I'm going to try a new share because I don't think y'all are seeing my notes and stuff. So I'm going to try it again. And then, see, I got everything working there. And try and see what happens. Everything seems kind of slow to me this morning. So I'll just wait for it to come up. Oh, I think it's going to come up. Yes. Okay. All right. You know, Dion knows that what I'm putting the videos on. I don't know. Has anybody watched a video, or just figure I'll watch it if I need to? But are they coming through okay?
Yes.
Everything's looking okay with them? Okay. All right. So tell me at this point if you've got any questions on the L'Hopital's rule stuff we did yesterday. It's not that hard. You have to be careful when you're differentiating and so forth, but does anybody having any issues or any problems you want to look at in that section? It was 10.
I have a question related to like something different.
Okay, what's your question?
So the quiz that's due today,
Yeah.
I tried doing number 2 and I could not do it to save my life. And I spent over an hour trying to figure out how to do it and I still couldn't do it.
What was the quiz? Wait a minute. What was it due today? No, wait.
The quadratic.
What was due today?
The quadratic on your screen.
Oh, the quadratic. Okay, yeah, I moved that. That's right. Oh, no, I didn't. It's due by 4/3. Tell me. I don't have that quiz in front of me. I'm not sure I know where it is loaded up. Let me see if I can give you a hint. Tell me what the problem was, Alexis. Tell me what the problem
was. The integral of x squared times the square root of 2x plus 1. And that's it.
Oh, okay. Listen carefully. This is not a complete the square kind of thing. It's just a miscellaneous substitution. So tell me what you tried. Alexis, you tell me, since your question, what did you try?
Well, first I tried making the u, like the stuff that was under the square root.
Uh-huh.
That didn't work.
No, it doesn't. What next?
I tried making the square root the u.
Okay.
And it didn't get me far.
I think it'll get you further than you think. I want to do the whole thing, or I may need to give y'all another miscellaneous, but that's actually what you need to do. Now you don't want to deal with that square root. So, and I think you had, I know what your problem is, I think. But how do you deal with the square root now? What do you do?
I squared it and got u squared.
You're on it. You're doing the right thing. Now, I will tell you that now you have already got this part substituted for. And you can find out what du is here from here. That's pretty easy. Okay, just take the derivative of that, take the derivative of that. The only thing that's hard at this point, and again, you've got all of that taken care of, because you can find du from this. You okay with that, Alexis, without me writing it down? Okay. The only thing you hadn't taken care of is that thing right there. But you want everything in terms of u. I contend that you have a way to find u or find x in terms of u here. What would you do to find x? If you wanted x, to see what x was in terms of u, that's what I would ask you to do if you were in algebra. I'd say solve for x.
I did that, but the x is squared, so I wasn't sure, like.
Oh, okay. That's not a problem. Okay, that's not a, if that's your problem, that's not a problem. Let me tell you why. So it would be -1 over 2 equal x, right?
Yeah.
Well, x squared is just that thing squared. So
See, I just wasn't sure we could do that because we never did that before.
yes, you can. You can do that. You know what u is, okay? I mean, you know what x in terms of u is, and you want x, you know, if you wanted x cubed or anything else, you could do that. You can do it. And then just, you know, what you're going to do is just put it right back in here and then square it all out and do the algebra on it. And it'll be easy to integrate after that.
See, I did that because I was like, I don't know no other way to get x squared. So I was just like, I'm going to do what you just did. So,
And that's
okay,
right.
I just needed that.
That's exactly right. That's
I was
exactly
not
right.
sure we could even do that. We've never done nothing like that ever. We did
Well-
something like what x cubed when we broke it up
Yeah.
and stuff, and there was something under the radical
Is
because
somebody's radio on or something? I can't, I'm having a hard time hearing. Something's in the background. Maybe it's, anyway. Yeah, but here's the deal, Alexis, and everybody. If you know what x is, you can, even if you had a 8x plus 1 up there, you could put that x in the place of it. If you had an x cubed, that's x. You know what it is. That's legal. That's x in terms of u. You can put it anywhere you want where there's an x. And then if you have to square it, you square it. And don't, and
I spent over an hour on that one problem.
well, and you were doing everything right. And because you don't have much experience, you didn't know what you could do and what you couldn't do. But I'm telling you that now, if you know what x is, you can put it anywhere you want in terms of u. Okay? So everything you did was right. Everything you did was right. Now just finish it up, do the algebra. Don't make any algebra mistakes while we're at it, okay? But it should be pretty easy to do now, okay? Is everybody else okay with that? So Kira, you said you got to that point and you said, well, I don't know if I'm gonna do it, but I'm gonna do it.
Yeah, I was going to do it anyway because I didn't know what else to do.
Dive in the pool, guys. Just do it. Deborah, what you okay with this one?
Uh-huh.
Okay. All right. Good. All right. So finish that one up, guys. And that's not too bad. But that's a miscellaneous substitution there. That's a miscellaneous substitution. Anybody other problems? How about L'Hopital's rule? How about that? How did that go?
I
Anybody?
didn't get to it. I'm being honest.
You didn't get to it? Okay, we're doing more of it today in a little bit different form. But anybody have a question that I can sort of do one? And if you had a problem that you didn't get answered. Let me look at, okay, I'm looking in 10.1, guys. And I'm looking at, what should I look at? I'm gonna look at 23, okay? Just to warm us up. Nope. On L'Hopital's rule, because we're gonna do a little variation on L'Hopital's rule today. If I do 23, I get the limit as x approaches 0 of e to the x minus e to the minus x, e to the x minus e to the minus x minus 2 sine x. 2 sine x. This is 23, and it's over x times sine x. So what's the first thing I do in a L'Hopital's rule problem? And now you got to talk to me today, so take your mic off and you can talk to me. What do I do first?
See if it's indeterminate.
See if it's indeterminate. See if it works. So if I plug 0 in here, that would give me 1. that would give me 1. The sine of 0 is 0. So 1 minus 1 minus 0 is going to be 0. So that's numerator does. The sine of 0 is 0. X is 0. That's 0. Okay, I'm good to go. Do the check first. So it's an indeterminate form. That means I can use L'Hopital's rule on it. So it's the limit as x approaches 0. Okay, L'Hopital's rule says take the derivative of the top. That's e to the x. Minus a minus here because the derivative of that will be plus e to the minus x minus 2, and the derivative of sine is cosine. All right, that takes care of the top. All right, guys, tell me what I need to do with the bottom just to make sure we're on board here. What do I need to do with the bottom?
Product rule.
Yes, product rule, exactly. So first times derivative of the second plus second times the derivative of the first, which is, I lost it, is 1. Mm-hmm. I get it right. First times derivative of the second, second times derivative of the first. Okay. Now I see if things will work now. Notice what I get is e to the 0 plus e to the 0 is 2 minus 2 times the cosine of 0. That's 1. 2 minus 2 is 0. I get 0 on the top. If I plug in 0 into the bottom, I get 0 times the cosine of 0, which is 0. Sine of 0 is 0. I'm glad I picked this one. It's just double duty here. It's still in L'Hopital's rule form, so I can use L'Hopital's rule again. So I'm gonna do that and see what happens. And it gets it can get a little messy, guys, but you just keep going. The derivative of that is e to the x. That one is e to the minus e to the minus x. Minus a minus, this will be plus 2 sine x. Down below, I need to use the product rule on that one. So x times minus sine x plus cosine x times 1. That's the product rule on that one. And then finally, the derivative of sine x is cosine x. All right, we are going to try again. So e to the 0 is 1, minus 1 will be 0. The sine of 0 is 0. I get 0 on the top. If you look at 0 here, it makes that one 0 because x is 0. The cosine of 0 is 1. The cosine of 0 is 1 here. 1 plus 1 gives me 2. That is not indeterminate, but what is 0 over 2? 0. That's the answer. So I had to use L'Hopital's rule twice. Now, guys, let me point out, and this happened yesterday if you want to look at it again, when I get something like 2 over 0, that's typically going to plus or minus infinity and the limit wouldn't exist. But 0 over 2 is just 0. So that's easy enough. All right, everybody okay? Try these. I think I said, gosh, there were a lot of these. I think I said 1 through 39, every other odd, but just do as many as you can and make sure you're getting the right answers, okay? All right, so let me go back and there's another, anybody got a question? Other question? What?
Like, I remember yesterday we said something about undefined. What's that again? I forgot.
That's the one I was talking about right down here, Alexis. If I got something that was 2 over 0, look at what happens. See, if something's getting closer and closer to 0, you're dividing by a smaller and smaller number, like 2 over a 10th would be 20. 2 over 100th. Notice I'm getting closer and closer to 0. That'd be 200. It's just blowing up. So that would be a case where, when you got a 2 over 0, that would be a case where it was either going to plus or minus infinity.
Okay.
Okay. All right. Everybody okay? All right. So I got this next section, which is just sort of it's using L'Hopital's rule, but it's looking at other indeterminate forms that can be put in L'Hopital's rule form. Now we can only use L'Hopital's rule on 0 over 0 and plus or minus infinity over infinity, period. So if something doesn't look like that, we got to say to ourselves, can I make it look like that? And the first thing I want to talk about is this indeterminate form, which is 0 times plus or minus infinity. Now, here's the idea. The idea with this is if something's going to 0, like that one, and the other one's going to infinity, if I flipped it sort of, now this is kind of this is bad form because you really don't talk about 1 over infinity, but if you were to put 1 over whatever was going to infinity, what would that be going to? If the denominator is getting bigger and bigger, what would that be going to?
0.
Yes. So if you do that, if you can flip a function that's not already, that's multiplied, you make it divided, you can usually get it in a form that's L'Hopital's rule. So let me show you generally what that says then. Look at this. It says we've got a function f of x times g of x, and that's what happens here. And suppose I get something like 0 times infinity. Suppose I get something like that. When I multiply two things together, I get 0 times infinity. What I'm going to do is take the one that's going to infinity if I want and put it as 1 over that. Now notice, just like I did here, notice that if you invert and multiply, you get the same thing back. So I'm not doing anything illegal. I'm just doing what I know I can do. The other thing is, if something's going to 0 and you put 1 over 0, that thing seems to be going to infinity. So you can flip either one of them and see if you can get it in L'Hopital's rule form. You'll see what I'm doing when I look at a specific example. And once I get it into the L'Hopital's rule form, once I get it either into 0 over 0 or infinity over infinity, it could be plus or minus there, plus or minus, then I'll just use L'Hopital's rule again. So here's what I'm going to do. Look at this example right here. All right, so we've got the limit as x approaches 0 from the right of x squared, which we know is 0. And the limit as x approaches 0 from the right of log x. I drew you a log x over here. Guys, you gotta have this in your head. Know what the log x looks like. It comes up all the time. As you approach 0 from the right of the log x, what is it doing? What's it doing? It's going to negative infinity. So here's that form, or at least one of those forms. It's going to 0 times minus infinity. When you see that, what you want to do is try to flip one of those functions so that you can put it as something over something else. You're setting yourself up to use L'Hopital's rule. So I think as far as being able, and remember what L'Hopital's rule says, you got to differentiate the numerator and differentiate the denominator. So I'm going to make the decision here that I want to flip this one because it's going to be easier to differentiate that thing than it is. That's not hard to differentiate, but it might work the other way, but I think I'll do it this way. Now, as we go to 0, log is going to minus infinity. As we go to 0 here, that's 1 over 0. That's what Alexis just asked me. What happens if you get like 2 over 0 or 1 over 0? That you're getting closer and closer to 0. You're divided by a smaller and smaller number. So that thing's going to infinity. That's exactly what I need because that's something I can use L'Hopital's rule on. So I am just rewriting the function to make it look a little different so it fits what I want it to look like. Okay, let's use L'Hopital's rule. Limit as x approaches 0, derivative of log x, take the derivative of log x is 1 over x. Take the derivative of 1 over x squared, well that's just x to the minus 2. So that derivative is minus 2x to the minus 3. Never let a chance to simplify go by. I simplified this by, one thing you could do, you guys, if you look at it, it's like minus 2 over x cubed. So I inverted and multiplied. Let me do it over here. I did a little algebra in my head there, guys. It was 1 over x times inverting and multiplying will be x cubed over 2, and I had a minus. So these x's right here canceled, and I got an x squared, and then I had the minus 2. So there it is simplified, just a little algebra. Now look at it. What's the limit as x approaches 0 from the right of this thing? That's easy. What is it?
0.
0 squared over minus 2, going to be 0. So I managed to use L'Hopital's rule in something that didn't look quite like it to begin with. Here's what I was saying earlier, though, just a few minutes ago. You could have written it like this, and it would have been, if you had put the 1 over the log x here instead of the 1 over the x squared. I think you probably could do it like this, but I think it's going to be a little harder. And the reason is this. If I had to take the derivative of that, I'd need to write it as log x to the minus 1. And that would be minus log x to the minus 2 times 1 over x. And it just got a lot uglier. And it might simplify, but you kind of pick and choose. If you start going down a road where it's looking nastier and nastier, just say, I'm going to go back and try something else. Just flip it the other way. Okay. So any questions on that page, guys? What I'm going to do is just more examples. You okay with that? Okay. So the next thing I'm going to look at is another one like that. We talked about this part of this yesterday. As we approach, I'm going to take the limit as x approaches pi over 2 from the left. If I plug in pi over 2 here, the 2's cancel, and pi minus pi is 0, so that was going to 0. Secant, on the other hand, is, if we looked at the graph of this the other day, I think, guys, it's going to plus infinity, I think. Pi over 2, it's going to plus infinity if I do that. Remember how I drew the cosine and then I flipped it and looked at it was going to infinity? That's what that is. And if you run into trouble here and you don't know what's happening, graph the function on your calculator and see what's going on. Okay, you got anything you want to look at there. Okay, so now I got this thing. It's not in L'Hopital's rule form, but I'm gonna see if I can put it there. And because it's kind of, this is tricky. This is really not tricky if you see it. I'm gonna try the secant there. I'm gonna put, in the denominator, I'm gonna put 1 over the secant. Because I invert and multiply, I get the same thing. But then I look at this and I say, oh, 1 over the secant, what's 1 over the secant? It's just the, what is it, guys? Just the cosine, isn't it? So in a way, I could have looked at this one and said, I could just drop that, the secant's 1 over the cosine, and I would have gotten a cosine down there. Now when I look at it, and I plug in pi over 2, the top's still 0. Cosine of pi over 2, remember the unit circle, up here at pi over 2, there's the point 0, 1, so the cosine is 0. So I got something I can use L'Hopital's rule on. 0 over 0. So that's what I'm going to do. I'm going to use L'Hopital's rule. The derivative of 2x minus pi is 2. The derivative of cosine is minus sine. Try it now. Once I've applied L'Hopital's rule, plug in pi over 2. I get a 2. The sine of pi over 2 is 1. And I already had that minus out there because of the derivative of cosine. When I use L'Hopital's rule. So the answer here is minus 2. Okay? So you just, when you get something times something else, try to write one as a flip in the bottom and see what happens. Okay. Now, another kind of indeterminate form. Sometimes,
Question.
yeah, Lexus, what?
So when we have something like that, when it's just like one type of trig thing, is it easier to make the trig thing the quotient?
You know, in this case, it made it easier just because the secant was 1 over the cosine, okay? I'm trying to think what this one would have done if you'd done the other way. This would have been harder the other way. It might have come out in terms of L'Hopital's rule, but when you put this one in the bottom, it's going to be easy to, sorry, I'm pointing at something you can't see. Right there, when you put this one in the bottom, its derivative is easy, but the derivative of this gets more complicated. What's the derivative of secant?
From secant tangent.
Secant tangent. So there you're sort of going down a road where you're thinking, it's getting worse. And not only that, but then you're going to have to think about more about what the trig functions look like, and harder trig functions. I mean, I have no idea what the secant times the tangent looks like as we go to pi over 2. I'd have to maybe get a picture of it or something. So if one thing starts to look like it's going south, go back and try the other one, because there are always two things to try here. Okay? Anybody else? Okay, so I'm gonna go up to another one. There are some other kinds of indeterminate forms. One of them is, and all of them, by the way, come from functions that look like this. When you have one function raised to another function. And these are truly indeterminate forms, guys. You might say, well, looks really weird. This one's indeterminate because you think, well, anything to the 0 is 1. But 0 to the 0, you're like, I don't know about that. Okay, so that's you don't want to think about it too hard. It's definitely an indeterminate form. Infinity to the 0, that's indeterminate. This one is the one that puzzles me the most sometimes when I think about it. You say 1 to anything is 1, but 1 to the infinity turns out to be an indeterminate form. You cannot think about it like that. You can't think about 1 to any power is 1 in this case. Now, let's talk about where these things come from. They come from problems where you got one function raised to another function. Now, think about what we've got to do to use L'Hopital's rule. To use L'Hopital's rule, we got to have something over something else. Well, that's a tough thing right there. I mean, how am I going to get something that was raised to a power to look like something over something else? The first thing I'm going to need to do is get that g of x down. What's something that you could apply to this so that you could get that g of x down?
Natural log.
Good, guys. That's natural log. That's exactly right. That's what we're going to do here. We're going to apply a natural log to it. We're going to go all the way through and get an answer, and then we're going to undo the natural log. And you give me a look ahead here. How do I undo a natural log? With an E. Okay, you got the process right there. Okay, so let's look at one. I'm going to spell out what the process is, and then we're going to look at some examples. Okay, so here's the method. And the method depends on log properties. I'm going to let the thing I'm trying to take the limit of be y. And then I'm going to take the log of both sides. And what that does for me, of course, is get a log y on the left. And because I have log of f of x to the g of x, I can bring the g of x down in front. That log property works for constants, it works for variables, it works for functions. You can bring it down in front. Okay. Now, what I'd like to do, now notice I've got something in a product form. I got something in a product form now. We're gonna investigate that. Okay. Okay. We're gonna investigate that because we know we just did one where we could fix that by putting it as 1 over something. We're gonna investigate that, and then we're gonna say if we come up with a limit of log y, which remember that's what that thing is. We took the log of it to get it to work. In the end, we'll take e to the L, and that'll be the answer. We'll undo that.
Wait, what does the L represent?
The L represents whatever the limit of that thing was. Suppose I found out what it was. If I find out what that limit is, I've got to undo the log on it. That's where I apply E.
Okay.
And sometimes these things will go to infinity. If it goes to infinity, then the original is going to go to infinity. If this goes to minus infinity, the original is going to go to 0. All right, let's do a problem. Because that's what's going to show you what we're doing here. Kind of hanging. I'll wait a couple of seconds. See if Deborah reappears. Okay. I think she went to open the door or something.
Oh, can you go back up?
Yep, sure will. So right, those are the rules. Okay, soon as Alexis quits turning her head back and forth, I know she's finished. Are you okay? Has everybody got it down? Okay.
Yeah.
All right, so let's go to an example. Oh, shoot. Rats. Yeah. All right, so I'm gonna go to, here's my example right here. Notice here, I have got one function raised to another function. This is exactly where you're going to use this method because you don't know what to do with that. You got to put it in another form. And we'll see if it's an indeterminate form. If x goes to 0, the inside goes to 1. If x goes to 0, that's 1 over something closer to 0. That's going to infinity. So this form right here, that thing is an indeterminate form. You looked what this went to, you look what that went to. Okay? That's my cue to use this method. So here's my first step. I'm going to take the function right there and take the log of both sides. So when I take the log of both sides, the log of the left side will be y. It'll be the log of this thing, and then I'll bring down the 1 over 2x. See, I sort of wrote it all together here, guys, but when I brought it down, it was just 1 over 2x. Okay. So are we okay on that, on the log property there? Everybody okay? All right. So now let's see what happens. If I let x go to 0 of this thing, see, that's the thing that we had, that's the log of y, and here it is right there. I'm going to look at it and find out what happens as x goes to 0. If you plug in 0 here, what's the log of 1? Think about your log graph. What's the log of 1? Log of 1, the log goes through 1, 0, yeah. Okay, that's what the log looks like. So that's 0. If you put in 0 here, 2 times 0 is 0. Okay, I'm in business now because that's something I can use L'Hopital's rule on. So let's use L'Hopital's rule. What's the derivative of the log of 1 plus 3x? Well, you put the 1 plus 3x in the denominator, and you put the 3 in the numerator. This 2x is not under the log, it's just a 2x. The derivative of 2x is 2. Now, we could simplify this if we wanted to, guys, but let's just try to plug in 0 and see what happens. If I plug in 0, I'll get 3 over 1 plus 0. So 3 over 1 over 2. This thing right here is that L. But that L was log y. That's what we had to do to it to make it look like I could use L'Hopital's rule on it. So if I get a 3/2, don't forget to undo the log. And when you undo the log, what do you get? If L is 3/2, what's e to the L? Yep, just e to the 3/2. I'm gonna pick another one at random and do another one like that. But I want to show you one more form, and then I'll show you a couple more examples. Okay. Is everybody okay with that? Let's see. Okay. Let's go up. There's one more indeterminate form. It's infinity minus infinity. This is hard to get your head around, but if you go far enough in math, you'll find out that there are different sizes of infinity, which seems a little weird. So I'll give you an example. If I say, suppose we look at all the integers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. That's an infinite set. Suppose I look at the even integers, 2, 4, 6, 8, 10, 12. That's an infinite set too. But it seems like a smaller infinite set in a way because the 2, 4, 6, 8 were actually included in the 1, 2, 3, 4, 5. So anyway, infinity minus infinity is indeterminate. Now, let me tell you something that's not indeterminate. Okay, infinity plus infinity is infinity. There's no way you can get around that. 2 infinities are infinity, so that is not indeterminate. Oh, run out of room. But that's not indeterminate. But this one is. Okay. Okay, so let's see what we would do. And you know what? With so many other things, as with so many other things, guys, the trick is to use some algebra on it. What can we use L'Hopital's rule on? Something over something else. So if I see two things that look like that, I'm just going to find their common denominator. Because if I find their common denominator, I will be able to maybe put it in form of L'Hopital's rule. So the common denominator here would be x and e to the x minus 1. That one needed an x, so I gave it an x. That one needed an e to the x minus 1, so I gave it that. When I subtract all this stuff, I get this, and I get that. And actually, I multiplied that out because I think it'll be a little easier in a minute. So I use the algebra on it to get it in that form. Now, plug in 0. 0 minus e to the 0 plus 1 is 0 minus 1 plus 1. That's 0. If I plug in 0 here, I get 0 minus 0 is 0. I've set myself up to use L'Hopital's rule. So if you see one like that, find the common denominator. Okay. Now I can use L'Hopital's rule. That means I take the derivative of the numerator, which is 1 minus e to the x here. What am I going to use on this thing, guys? What am I going to use on x e to the x? Remember, I'm taking the derivative here. Product, exactly. So that's first times the derivative of the second plus second e to the x times the derivative of the first minus, oh, what? Did I make a mistake? I made a mistake. No, I didn't. Well, I did something that I went on to the next step and got it right in the next step. That sound familiar, Tiara? Okay, let's do this right. Hang on.
It sounds like me.
Yeah, I do it too. Okay, so, oh, that was an X. Whoops, that's okay. So the derivative of x, that thing right there, guys, already when I take the derivative, it should have been 1. So that's 1. Okay, sorry about that. Okay, so so now when I look at it again, and I plug in 0, I get 1 minus 1 because e to the 0 is 1. This is 0. That's 1. 1 minus 1 is 0. Whoops! I got it again. I got to use L'Hopital's rule again. Hey, Deborah.
Hey, sorry.
That's okay. You can watch it, or we may have extra time. Let me see. I made a mistake right there. Okay, so I got to use L'Hopital's rule again. So as you approach 0, we get 0 over 0 again, so I'm going to use it again. Derivative of the numerator is minus e to the x. Derivative of the denominator, I'm going to have to use the product rule on that again. So that's what this is again. And the derivative of e to the x is e to the x. And see, I made 2 mistakes. The derivative of minus 1 is, that's gone. Okay, that was, I had made the mistake and it made it into another mistake down here. So now, I'm going to try again to plug in 0. I'll get minus 1. That drops out because 0 times anything is 0. E to the 0 is 1, plus e to the 0 is another 1, and 1 plus 1 is 2. I'm done. Okay, I'm done. And Deborah, just because you came in sort of right in the middle of this, I was using L'Hopital's rule right here, and I made a mistake. The derivative of x is minus 1, so I had an x there, and then it made me miss that too. So I should have caught it when I did it, but I didn't. Okay. Okay, I'm gonna pick a couple of random problems. We got a little bit of time left. We got about 10 minutes left. I'm gonna pick a couple problems, maybe that sort of look like some of these things, and see what we can do with them. Is everybody okay on that one? Because I did mess it up. All right, let me go to the book and see if I can do some more. Let me get rid of, I don't need to get rid of it. I got another sheet here. Okay, this stuff, guys, is in 10.2. It's called other indeterminate forms, but the reality is they're just other forms that you can change into a L'Hopital's rule form. Let's do the limit as x approaches 0. Oops. the limit as x approaches 0. Ugh, starting out bad here. Let's get rid of that. Ugly. Limit as x approaches 0 of x to the x power. That's a funky looking function. Okay, it's x to the x. You know, we've seen our technique here before. If I call that y, we need that x down below. So what did we say we were going to do? What did the technique say we were going to do? Take the log, right? So what we're going to do is say we're going to take the log of both sides. And that log, because to the right of 0 is continuous. We don't have a problem with that. We can bring it down. So that's going to be x log x. Okay. So essentially, if y, I really should have let just y be x log x here. So what we want to look at is this thing right here. All right. So actually, I'm going to erase something here, guys. I don't like the way I've got this written. I don't. Let's just do this. I want to let the function be x to the x. So y is x to the x. I'll take the log in the end, and the log's going to 0. So that's going to be that. Now, I'm going to try to use L'Hopital's rule on this thing. And since it's a product, and by the way, we're going to 0, that's going to be, x is going to be 0. And remember that log x, and I'm sure it said 0 from the right. Yep, 0 from the right. If you're coming into the right, the log x is going to minus infinity. So this form is 0 times minus infinity. Okay? So I want to rewrite this. That means I'm going to put 1 over this or 1 over that in the denominator. And for this reason, the same reason I did it a minute ago, I think I'm going to leave the log x in the top and the 1 over x in the bottom. Okay? Now, let's see what happens to that as x goes to 0 from the right. If we go to 0 from the right, that's minus infinity. 1 over x, think about what 1 over x looks like. 1 over x looks sort of like that. So as you go towards 0 from the right, that's going to be infinity down there. Okay? So it's something I can use L'Hopital's rule on, and that's what I'm going to do. So I'm going to take the limit here as x goes to 0 from the right using L'Hopital's rule. So what's the derivative of log x there, guys? That's the top. What's the derivative of log x? 1 over x. And in the bottom, this is just x to the minus 1. So it's going to be minus x. Minus 1 to the x. Darn. Hang on. Minus 1 x to the minus 2. Okay. So do a little algebra on it. The whole thing's going to be minus. So it's the limit as x approaches 0 from the right of minus. If the x squared jumps over here, up there, it just leaves me with an x, because x squared over x is going to be x. Tell me what's happening as x goes to 0. What's minus x doing as x goes to 0 from either side? What's x doing as x is going to 0?
0.
0. Going to 0. Okay? So everybody see, it's just like plugging it in. Now, the temptation is to stop right there, but that's not the answer. Why is that not the final answer, guys? Because the log. That's right. So I've got to undo. That's the log of the limit. Okay? So what's the answer then? If I want to undo whatever the log of that thing, it would be e to that thing.
1.
Whatever you get here, it'll just be e to that thing. Okay? Let's see if I can find one more. What if I had this one? Does everybody have that? That's kind of sloppy. I don't like this. Me and my pen are not getting along well today. But suppose I had this one. This is 42 on page 504. The limit as x goes to infinity of the log of 4x plus 3 minus the log of 3x plus 4. Now, guys, if you remember from pre-calc, these are just logs that got shifted. They still look like that general thing, but they get shifted one way or the other. So, for instance, the domain of this one, that's got to be bigger than 0 for the log to be defined. So bigger than 0, that means x is bigger than minus 3/4, which means that asymptote right there is at minus 3/4. You may remember that from pre-calc. The point is, if the graph still looks like that and x is getting bigger and bigger, what is the log of x doing? Where's it going if x, you're taking the log of something bigger and bigger?
Infinity.
Infinity. You see that on the graph? The y-values are just going up. Same with this one. So it's infinity minus infinity. Now, I told you to use some algebra, but I mean, or some pre-calc. Tell me, I need this to look like a quotient, guys. How am I going to make this look like a quotient instead of infinity minus infinity?
There's a log property.
Yes, there's a log property that puts those two things together, aren't there? If I get this, so I get the limit as x goes to infinity, that's the log of 4x plus 3 over 3x plus 4. Now, an interesting thing happens here, guys. I may not even have to use L'Hopital's rule at all. Because if I look at this thing, think calculus 1, guys. When you had an expression that had powers of x in the denominator and the numerator, and we went to infinity, do you remember what happened with a limit like this?
Coefficients.
Yeah, look at the coefficients on the highest power. If the powers are the same, the limit would be exactly the coefficients on it. So yeah, it's 4/3. And I've copied that. That's a 4. All right, that's 4/3. So the answer to this is I don't have to use L'Hopital's rule. It's just the log of 4/3. I only used a property of log. I didn't have to take a log to get a power down or anything. So a lot of times they'll just throw these into the homework problem and see if you're paying attention. Because you know what? When I looked at that, I was like, that's not a quotient. That's the log of a quotient. So I'm thinking I'm a little stuck as far as L'Hopital's rule goes. But maybe I can do it another way. And the other way is remember what happens to this thing. It goes to 4/3. So the answer is log of 4/3. Now, let me take a few minutes, guys. I am done with what's going to be on this next test. This is the last thing. I do want Monday to answer for you to catch up with things over the weekend with L'Hopital's rule in this part here. So I want Monday to answer questions on anything that might have surfaced as a problem in all of these things over the homework. That includes integrals. That includes L'Hopital's rule, just anything that you're having a problem with on Monday. My instinct, based on what I heard you here say yesterday, is to have the test ready to go, and so I could post it Monday afternoon and have it due by Wednesday morning class time. What's that sound like to you?
You say that one more time.
Okay, I will post it Monday. I will take questions. I might start, anything I start new on Monday will not be on the test. This is it for the test, okay? Integrals and this. So as soon as we finish class on Monday, as soon as I can get it posted, I will post it. I have it posted by 5 on Monday. And then you have until 11 o'clock on Wednesday to take it. We will not have class on Tuesday because that's your test day. So you've got the span of time in there from Monday afternoon to Wednesday morning to take the test. Open book, open notes, so on and so forth. Does that sound reasonable? Does that sound what you kind of thought? Maybe keep you away from some of the other stuff you're having the end of next week? You're muted, Alexis. I can't tell if you're thinking or talking.
Yeah.
That's okay. Deborah, how about you?
That's good.
Okay. Tiara, thumbs up or not?
I can work with it.
Okay. All right. Somebody tell Dion for me. I'll send out an email, but you can talk to Dion, Alexis.
Yeah.
Okay. Tell her that's what we decided. Tell her to look at the video I'm going to post here and work on these 10.1 and 10.2. Test cutoff is right here. Test cutoff's right here.
So I have a question. When is the improper intervals quiz due?
No, that when I put that on the syllabus, let me look at the syllabus. I put that on the syllabus for Monday. If I even get to start that, none of it will be on the test. None of that's going to be on the test. Okay?
All right.
So the first thing I'm going to ask Monday morning is somebody, what don't you understand? If you got some problems, or you got problems you got stuck on, like Alexis spent whatever, an hour on that other one, but it wasn't as bad as we thought. We'll take care of that stuff. And if I don't get to any of this, I'm not going to cry any tears over it. I'll move it till after that. I'll move it to Wednesday. So don't worry about that. Now, the quadratic quiz is due tonight. Yeah, that's due later tonight. And I think most, have y'all about finished that or started it? I know you started it because Alexa started it. Deborah, you okay with that?
I haven't really started it much except
Okay.
for that one you
All
mentioned.
right. It shouldn't be too bad. I will not have a chance, if I do the test like this, I will not have a chance to give you a quiz on L'Hopital's rule, but if you, that means you just need to look at the homework and see if you're having any problems on the homework, okay? The answers are in the back, and there's plenty of them. There's like 40 of them there in both sections. There's a lot of them. So check the answers in the back. You don't get to check the answers in the back, we need to talk about it. Okay. Have a nice weekend. Anything else I need to know before I sign off, guys? Except I can't find out. Okay, there's where I'm signing. Okay. I will see you Monday morning. If anybody's got a question that you're losing sleep over, don't do that. But if you got a question you got losing sleep over, just email me and I'll try to email you back and give you a little hint or whatever I need to do. Okay? All right. Bye. Have a good weekend.